So, day before the last day, I think I'm going to build on Twitch and YouTube the next app that I'm going to make. And so I'm going to finish up this series um, well, not finish it up, but I'm considering just live streaming my dev journey and the coding process and setting up for the actual development of the app and all. I think I am going to have to choose a different app. But if you're joining me for the first time, I'm Christina. I am reviewing some code stuff for 28 days, which ends tomorrow. And I am very tired of doing this every day at this time. My brain works better in the morning, so I think I'm going to start I've never streamed on Twitch, but I think I'm going to start a Twitch channel as well as um, I've never used Twitch, but I think it's a streaming platform, right? So I think I'm going to stream a lot of stuff on Twitch and uh, maybe even play games. Um, Hold on. So I'm going to finish this out and so I'm going to speed this up to 1.5 and we're going to listen and learn and hopefully digest this. Because I don't learn in the evening times, but I have to stream in the evening times. We're only going to finish the AA linked list. If you missed yesterday, you can see his code in GitHub that he linked here. And you can see the actual Python and C++ versions. This is Java. I dislike Java, but this is Java. Um, but I am going back through some of the algorithms. So we're going to start here today.
Or at the end of the linked list. And we throw a runtime exception if the list is empty, because it doesn't make sense to peek an empty list. Okay, now we get to the first more complex method, which is remove first. So this is if we want to remove the head of the linked list. So we can't do much if the list is empty. Otherwise, we get the data, we extract the data at the head, and then move the head pointer forward. We decrease the size by 1. So if the list is empty, we set the tail to be null as well. So both the head and the tail are now null. Otherwise, we deallocate the memory of the previous node that we just removed. This is especially important if you're in C or C++. Make sure to free or delete your pointers. Then at the end, we return the data. A very similar thing is done for last, except we're using the tail this time to remove from the tail of the linked list and not the head. Okay, and here's a generic method to remove an arbitrary node. Remark that I set this to private because the node class itself is private, so the user shouldn't have access to the node. That's just something we're using internally inside the linked list data structure to manage the list. So if the node that we're removing is either at the head or the tail, detect that and call our methods either remove first or remove last. Otherwise, we know we're somewhere in the middle of the linked list. And if we are, we make the pointers adjacent to our current node equal to each other. So we're effectively skipping over the current node. And then, of course, don't forget to clean up your memory and return the data. So we have to temporarily store the data, of course, before we delete the node. Otherwise, we've deleted the node and the data is already gone. Now, suppose we want to remove a node at a particular index in our linked list. Yes, we can do this. Even though our nodes are not explicitly indexed, we can pretend that they are. So first check that the index is valid. Otherwise, throw in a legal argument exception. So here, we are trying to be a bit smarter than just naively going through the linked list. Either we're going to start searching from the front of the linked list to find our index, or from the back, depending on if the index is closer to the front or to the back, although this method remains linear. So for the remove method, we want to be able to remove an arbitrary value from our linked list, which is object. So we're going to also support searching for null values in case someone decided that the value of the node should be null. that's fine. So we check that special case. Otherwise, we traverse through the linked list until we find a null element and then remove that node and return true. We return true if we actually found the element we want to remove. Otherwise, we return false down here. In this else statement, we search for the element we want to remove. We use the dot equals method to check if we found the element. If so, remove that node and return true. Okay, here we have a related method, which is index of. So this is not remove at an index or remove a value, but get whatever index this object is at. Again, supports searching for null. So even if our value is null, we'll just return the first place we find a null element. So again, traverse the linked list. Otherwise, search for a non-null element and also increment the index as we go. We can use the index of for our method contains to check if an element is contained within a linked list, because we return -1 if the element is not found. Something that's useful sometimes is to have an iterator for a linked list. This is also trivial to implement. Just start a pointer, traverse at the head, and traverse until you reach the end. Notice I'm not checking for concurrent modification error, but if you want to, it's pretty easy to do that. And lastly, at the very bottom, we have the toString method to print a string, or to get rather a string representation of our linked list.
If you look around, everything is inspiration. My best friends and I own Pirate Worldwide. We're on a mission to discover as many ideas as possible.
May I begin by saying that the stack is a remarkable, absolutely remarkable data structure. One of my favorites, in fact. This is part 1 of 3 in the stack videos. Part 2 will consist of looking at a stack implementation, and part 3 will be some source code for how a stack is implemented using a linked list. So here are the topics that we'll be covering in this video, as well as the others. First, we will answer the question about what is a stack and where is it used. Then we will see some really, really cool examples of how to solve problems using stacks. Afterwards, we will briefly look at how stacks are implemented internally and the time complexity associated with the stack's operation. And lastly, of course, some source code. Moving on to the discussion about stacks. So what is a stack? A stack is a one-ended linear data structure which models a real-world stack by having 2 primary operations, namely push and pop. Below you can see an image of a stack I have constructed. There is one data member getting popped off the top of the stack and another data member getting added to the stack. Notice that there is a top pointer pointing to the block at the top of the stack. This is because elements in a stack always get removed and added to the top of the pile. This behavior is commonly known as LIFO, or last in, first out. Let's look at a more detailed example on how a stack works and how things are added and removed from a stack. So let's walk through an example. On the left side, I have some instructions on what we need to add and remove to the stack. So the first operation is a pop. So we remove the top element from the stack, which is apple. So boom, apple is gone. Now we push onion onto the stack. So we add onion to the top of the stack. Next instruction says to push celery onto the stack. Next is watermelon, which we put on top of the stack. The next operation says to pop, so we remove the element at the top of the stack. This is the watermelon we just added. The next operation, also a pop, so we remove from the top of the stack. This is celery. And the last operation, push lettuce onto the stack. So we add lettuce on the very top of the stack. So as you can see, everything operates on the top of the stack. We don't have access to anything else but the top of the stack. This is critical in our understanding of how a stack works. So when and where is a stack used? Stacks are surprisingly used absolutely everywhere. They're used in text editors to enter text you've written, in browsers to navigate backwards and forwards. They're used in compilers to make sure you have the correct number of matching braces and in the right order. Stacks are used to model real-world stacks, such as books, plates, and even games like the Tower of Hanoi, which we'll get to shortly. Stacks are also used behind the scenes to support recursion by keeping track of previous function calls. When a function returns, it pops the current stack frame off the stack and rewinds to the next function that is on the stack. It's rather remarkable that we use stacks all the time in programming and never even notice it. Something else you can use stacks for is to perform a depth-first search on a graph. A depth-first search can be done manually by maintaining your own stack or by using recursion. Well, guess what? Both use stacks, as we have just discussed. Complexity analysis. So the following complexity table assumes that you implemented a stack using a linked list. Pushing takes constant time because we have a reference to the top of the stack at all times, while the same argument goes for popping and peeking. Searching, however, still takes linear time. The element we're searching for isn't necessarily at the top of the stack, so we may need to scan all the elements in the stack, hence requiring linear amount of work. Now here's a cool example of a problem using stacks. Problem. So given a string made up of the following brackets, round brackets, square brackets, curly brackets, determine whether the brackets properly match. So analyze the examples below to understand what type of bracket sequence is valid and which ones are invalid. So before I show you the solution, try and come up with a solution yourself. Hint, use a stack. Okay, in this first example, consider the following bracket sequence. As we are processing the string from left to right, I will be displaying the current bracket and the associated reversed bracket. So let's begin.
Go.
For every left bracket we encounter, we simply push those on the stack. So this is a left square bracket that I've highlighted in light blue. So we push this one on the stack. Same goes for the next left square bracket and for this left curly bracket. Okay, this is a right square bracket. So we encountered a right square bracket. So we need to do two checks. First, we check if the stack is empty. If so, the bracket sequence is invalid. But if there are still things in the stack, then we pop the top element and check if its value is equal to the reversed current bracket. Right now, the top element is equal to the reversed bracket, so we are good. Next is a right square bracket again. So is the stack empty? No, it isn't, so we're good. Is the top element of the stack equal to the reversed bracket? Yes, it is, so let's keep going. A round left bracket, let's push it onto the stack. A right bracket, is the stack empty? No, okay, so we're good. Is the top element of the stack equal to the reversed bracket? Yes, okay, so we're good. Another right bracket, is the stack empty? No, okay, good. And is the top element of the stack equal to the reverse bracket? Yes, okay, good. And now we're done processing the string. We need to make sure the stack is empty now. Why is that? Well, in case the last few characters in the bracket sequence were left brackets, they would still be in the stack, right? But our stack is empty, so we can conclude that this bracket sequence is indeed valid. All right, let's do another example with another bracket sequence. So try and work this one out. So the first bracket is a left bracket, so we push onto the stack. The second bracket is also a left bracket, so we push onto the stack. This next bracket is a right bracket, so let's check if the stack is empty. No, it's good. And is the top element of the stack equal to the reverse bracket? Yes, it is. This next bracket is a right bracket. Is the stack empty? No, so we're good. And is the reverse bracket equal to the bracket at the top of the stack? No, it isn't. So this bracket sequence is invalid. So here's the pseudocode of the algorithm we just ran through. So if we let S be a stack, then for every bracket in our bracket string, we can get the reversed bracket for that current bracket easily. So if our bracket is a left bracket, push it onto the stack. Otherwise, we check if the stack is empty and if the element at the top of the stack is not equal to the reversed. If either of those conditions are true, then we return false. Otherwise, we return whether the stack is empty or not. And if it is empty, then we have a valid bracket sequence. Otherwise, we do not.
Yeah.
I want to take a moment and look at the Tower of Hanoi, a very popular game amongst mathematicians and computer scientists, to see how it relates with stacks. The game is played as follows. You start with a pile of disks on the first peg on the left, and the objective of the game is to move all the disks to the rightmost disk pile. At each move, you can move the top disk of any pile to any other pile with a restriction that no disk can be placed on top of a smaller disk. So we can think of each peg as a stack, because we're always moving the top element in a peg and placing it on another peg. So shall we play? I will let the animation run, and you will see how each peg acts like a stack. It's pretty cool.
Top first, first stack, second stack. First stack.
So you just saw how transferring elements from one peg to another is exactly the same as popping a disk from one stack and pushing that same disk onto another stack, given that the disk you're placing on top is smaller. So that's really cool. Welcome to part 2 of 3 in the stack series. This is going to be a short video on one way to implement a stack. So stacks are often implemented as either arrays, singly linked lists, or even sometimes doubly linked lists. Here I will cover how to push nodes onto a stack with a singly linked list. Later on, we will look at the source code, which is actually written using a doubly linked list. Okay, to begin with, we need somewhere to start to begin our linked list. So we're going to point the head to a null node. This means that the stack is initially empty. Then the trick to creating a stack using a singly linked list is to insert the new elements before the head and not at the tail of the list. This way, we have pointers pointing in the correct direction when we need to pop elements off of the stack. As we will soon see, the next element, however, we need to push onto the stack is at 2, so let's do that. So we create a new node, adjust the head pointer to be the newest node, and then hook on the node's next pointer to where the head was before. And we use the same idea for 5 and also 13. Now let's have a look at popping elements. This isn't too hard either. Just move the head pointer to the next node and deallocate the last node. So here we pop the first node off the stack and set the node's reference to be null. So that will be picked up by the garbage collector if you're coding in Java, and it will since there are no other references pointing to it. If you're in another programming language that requires you to explicitly deallocate free memory yourself, like C or C++, now is the time to do that, or you will get memory leaks. Getting a memory leak in a data structure is one of the worst kinds of memory leaks, especially if it's a custom data structure that you intend on reusing. So keep watching out for that, not only in this video, but in all the data structures that we will be covering. If you see in an implementation that I'm not correctly cleaning up my memory, please point it out to me, or send a pull request to the GitHub repository so we can patch that. Okay, so we keep proceeding by removing the head and advancing the head pointer down to the next node. Pop again, and pop again. There we go, we've stopped popping, we've reached last node, and the stack is now empty.
Want a new career but don't have experience?
Prior to the Google UX design certificate, I didn't have any experience in.
Welcome to part 3 of 3 in the Stack series videos. Today we'll be looking at some source code for a very simple stack. So the source code can be found at github.com/williamfizet/data-structures. Make sure you understood part 1 and 2 of the stack series before continuing, so you actually know how we implement a stack using a linked list. Also, if you like this video series and the implementation of the stack data structure I'm about to present to you, then please start this repository on GitHub so that others can have an easier time finding it as well. Here we are in the stack source code. This is an implementation in the Java programming language. So the first thing you may notice is here I have an instance variable of a linked list. This is the linked list provided by Java. In fact, it's a doubly linked list provided by Java. This is the linked list they provide in their package java.util that I will be using today instead of the one that I created in the linked list videos. This is just for portability in case you want to use this stack for whatever reason. So we have two constructors. We can create an empty stack, or we can create a stack with one initial element. This is occasionally useful. This first method, we can get the size of the stack. So to do that, we return the size of the internal linked list with all the elements of our stack. Easy. We can also check if the stack is empty by checking if the size is 0. So this next one is just push. So to push an element onto the stack, we just append that element as the last element in our internal linked list. Easy enough. We can also pop an element off the stack. So to do this, we check if the stack is empty. If it is, then we throw an empty stack exception because we can't pop an element off of an empty stack. That doesn't make sense. Similarly, the same thing with peek. We can't observe what the top element of the stack is if the stack is empty. And if it's not, then we can peek the last element of our list. And lastly, we can return an iterator to allow the user to iterate through our stack. This iterator returns an iterator for our linked list, which supports concurrent modification errors. So this was a really, really quick implementation of the stack. It's only like 50 lines of code. Let's talk about queues.
Nope, not moving on. I feel like if I don't do things, then it's just watching the video over and over and hoping for something to change. So I don't want to do that. I want to pull up, actually let's look at problems. And I want to look at stack and see if I can find simple stack problems. And it's easy. Let's get rid of that. There we go. So how did I solve this one? Yeah, so this is the one he was just talking about. So I'm going to redo this one. I did this before, but we're going to redo it. And I'm going to go back and look at his pseudocode.
Welcome to part 3 of 3 in the stack series videos. Today we'll be looking at some source code for a very simple stack. So the source code can be found at github.com/WilliamFizet.
There we go.
Welcome to part 2 of 3. At the top of the stack. No, it isn't. So this bracket sequence is invalid. So here's the pseudocode of the algorithm we just ran.
Okay. We're going to create a stack. And after you create a stack, we'll say for bracket in one, two, three, four, five, six. Okay. Get reversed bracket. Four. Okay. Not sure what this line is. I think I have to make a. And actually, I'm gonna say, now we'll leave it back. Like, if bracket in, let's say all the left bracket. Left bracket, stack dot push bracket. Else if stack dot is empty or s dot hop not equal to the reverse bracket, return false, return true. And now what we're going to do here is bracket underscore strings Okay, so we have those set up. So now let's do create rev. Rev equals get reversed bracket. So I need to create code that gets the reversed bracket. Let's create a function def reverse underscore bracket. Okay, and it's going to pass one bracket at a time. We're going to call that B. And if B equal Actually, I'm not taking into consideration anything that's being passed. I need to redo the whole top part. Okay, so this is wrong. I'm going to set this up right first. This goes here. Oh, we need left right here. Okay. So string is what's being passed. This is the function I created for bracket in. This is the string. There we go. Now, let's run this code. Equal. Oh yeah, I always forget that. And apparently I forget these too. Type object not iterable. Oh, this should be S. This object has no attribute push. Oh, that should be append. This should have, let's see. If not. Okay, we'll try not. If not stack. String has no attribute pop. Oh, this should be stack. False is not defined. Capital F's, capital T's. Okay, we got one. It's better than my first try doing this. Okay. Oh, hold on. Stack empty. Got it. Same difference. Okay, so something is definitely not correct. It's not doing, so it's doing this third use case. It's catching all of the wrong ones. It's not catching any of the right ones. Which means this is a slightly different problem. Let S be a stack for bracket NS, which is that string up there at the top. The reverse of the bracket is reverse bracket, bracket, which is what I put in, and it reverses this. So if the given bracket is that, it returns the other one. If okay, let's do these things. Let's start with print. Um, okay, and let's get the reversed. And let's just make sure those are printing correctly. Aha. This was the input, but it's making up other stuff. Why is my code making up stuff? It should have stopped. So something's wrong with checking that this is all done. Yeah, something's wrong with checking because it should have stopped iterating. So what is it doing and why hasn't it stopped iterating? It seems to keep calling reverse bracket for bracket NS. So why is it not stopping? These are wonderful questions. I have no answers to. Like, where is it coming up with this? Because this would be false. So something's happening here that I don't understand. It's not catching. I think that stack is empty. Let's see. Let's check for the length, and length is 0. Let's try that. Nope, still not catching that it's 0. I actually don't know where to look for a problem. They say it's easy. It's not easy, especially when I don't understand where the uncount um, it's not catching it either. The only other way. Okay. Let's do this. I'm going to stack pop. I'm going to say P equal stack pop. Print P. We're going to put P here. And we're going to still say not step. Okay. Syntax error. So P can't equal. Okay, let's check Python. Yeah, that should be correct. By pop, that's a string and it's to string. Let's do it this way. It's not popping the right thing. Because it's not going to equal reverse. Mm. Okay, I'm stopping here for today. I'm going to go do some debugging. Y'all have a great evening.